So when you see the whole thing here, this is what you're going to see here. This is the whole chart of the nuclides. Way down there, you're going to see hydrogen started. And this is where we're going. We're going down there to see where it all began. See here, some notes there. I need the hand to move it. Actually, we're going to zoom one more time there. This is where it is, right here. So, the elements. We'll get to Glenn Seaborg and his great discoveries of plutonium and other things. To begin with, the periodic table, as it is now known, in its modern form, you can thank Mr. Glenn T. Seaborg for. The elements are listed in a way that the atomic number, the number of protons, goes in order as they get bigger and bigger and bigger. Noble gases don't react with anything except there's a row of 2 at the bottom. And there's now an element named Seaborgium in honor of Glenn T. Seaborg. Right there he is. So Glenn discovered plutonium at the University of California in Berkeley, 1941, after Macmillan, who went to Chicago, had just discovered neptunium. They took uranium, and we're going to see that reaction. That is at the top of the chart of the nuclides. What we have is the beginning. How did it start? When you see the history of the universe and how elements were dispersed, hydrogen, the universe still is predominantly hydrogen. All the mass you'll hear at a star is hydrogen, hydrogen. The sun, hydrogen, right? Well, when we see the way that our star makes helium, stars many generations ago, 3 to be exact, I guess they say now, a star exploded that had so many different layers of magnesium, calcium, there's silicon layers, there's all these different layers, the simple neons and all those heliums. So as they expanded, supernova, bigger elements were made. Iron has an energy curve that iron, cobalt, nickel are the 3 they say are the biggest elements a star will make before supernova. We'll see that there's a neutron window to bismuth 209 that'll make stars in an atmosphere, not even in the core with fusion anymore. But there are other wonders that I wondered about, and that's what I'm here to share with you today. When we first see that stars are made by fusing hydrogen to helium, the astronomers skip over the first step. They say 4 protons, if they even say protons, we're lucky. 4 hydrogens. To be a hydrogen atom, you need the electron with the proton. 4 hydrogens make helium. Now remember I said the periodic table lists elements in order of their protons. That's the atomic number they call it. So hydrogen, number 1, if you took 4 of those, 4 times 1 is 4. What's the atomic number of helium? 2. There's 2 protons in a helium-4 nucleus. What else is in there? With a mass of 2, these are things called neutrons. Some of you that haven't heard of that before, don't worry about it. We're just going to count them. We'll pretend we know what they are. We're going to find later they're quarks combinations. I'll say it again so it echoes. 2 ups and a down is a proton, 2 downs and an up is a neutron. I guess we're going to digress from here. This is how helium-4 is made. 4 protons, when we see the quark combination before we saw, but you haven't, so later we will see 4 protons. The first 2 come together, a proton is turned into a neutron. Now you have 1 proton, 1 neutron. This is known as heavy hydrogen. There isn't very much of it around. That's why this table here is drawn to the abundances, so it's tiny. There's even another one that has 2 neutrons and 1 proton, but it's still hydrogen. 1 proton. How do 4 protons come together to make 2 neutrons? 2 protons. See, it's confusing me. This is why I came up with this. This technique, when you understand hydrogen to helium, everything else on top of it follows the same scheme. So, In order for two protons to come together, a neutron is made. There's actually antimatter that comes out of that reaction with the mass of an electron, so it's called a positron. And there's a tiny little neutrino. We'll see those reactions later. Now we're just showing the trends. Two proton-neutron combinations come together, or what they say, a proton and a neutron, which is called deuteron, will get hit with another proton. So then you'll have two protons and one neutron if they stick together. That's the helium-3. But in the core of the sun, there's still all these other hydrogen protons bombarding it, that when another, see, that's why it can't fit that way. It's got to be the proton and the neutron together, the deuterium with the electron, but there aren't any electrons. So deuteron, the proton, the neutron, another deuteron has to combine with it in order to make a helium-4, which is known as the alpha particle. I was trying to find some stuff on Ernest Rutherford before. This is a simple reaction when he was hitting alpha particles into a nitrogen atom, and I couldn't even find it on the internet. So we're going to learn how, after helium, two heliums would be beryllium-8. There's nothing in beryllium-8's box here, is there? What happens is a triple alpha process, they call it. Hans Bethe discovered this. He came to this conclusion on a train ride, I guess is the famous historical aspect of that. Three alpha particles. Two come together, a beryllium-8, you'll see it with a little asterisk, high energy. We're talking microseconds, I know, nanoseconds, I'm not even sure, but so fast that as soon as those two come together, if another alpha hits it, it'll go over an energy barrier to the point where carbon-12 is now a stable molecule. Stable nucleus, 6 protons, 6 neutrons. Carbon-12, carbon, most life-essential element, most people call it. Anything organic chemistry, is going to have carbon as its main atom. So carbon is made in stars. I'll tell you a story. This is why I got into physics anyway. After I got my degree in chemistry, I thought, organic chemistry. I studied for 2 years, another year of biochemistry. I didn't know where carbon came from. Where does it come from? Our sun is fusing protons to make helium. Not enough energy to fuse 3 heliums to make a carbon. What you need to do that is a star at 100 million degrees. Jupiter, the orbit of Jupiter, there's a star whose atmosphere goes that far out. It's called Betelgeuse. Astronomers will tell you, oh, it's a red star, it's cool. Well, in the core, since that star is so humongous, all you see is the red light on the outside coming. It's hot on the inside. So a triple alpha process is nothing. 100 million degrees. So in order to fuse carbon, you need higher energy, hotter temperatures. Our sun is still, right now, fusing the protons to heliums that some other star had done earlier. Because as I tell you, our bodies, we are older than the sun. And I'll say God. God made us way before the sun started even spitting light out, okay? Well, I don't know about that, but the elements he made, okay? The elements, carbon, again, was made in a star that our sun isn't hot enough to make. Hey, maybe our star once did, and now it's just shrinking in. Maybe things work backwards. You never know. Or do you? People tell you they know. So maybe our star once was bigger and made elements like iron, and then got smaller in carbon. Now it's just making helium for light. But anyway, the process of what they call binding energy above iron, and I'll call it iron, cobalt, nickel. If you look on the periodic table, these are called noble metals. Right here in that big gap there, you're going to see iron, Fe, Latin for ferrous, cobalt, nickel. These elements are fusing inside the cores of stars. So that's how elements are made. Now,